Welcome to the workshop. Today we want to take a look at section 3.5, multivariate distributions. In the past 4 sections, what we've taken a look at are discrete random variables and continuous random variables, talking about their distributions. So we talked about probability distributions and the conditions for a function to be a probability distribution. And then we also took a look at probability distribution functions. Which are also called the cumulative probability distributions. So we looked at that for, those are the discrete random variables, and then for continuous random variables, of course, it's called a density function, or a probability density instead of a probability distribution. So, so we can still have the cumulative probability distribution, and then we, of course, can take a look at conditions for a function to be a probability density as well. But we're going to take all of those things and revisit them here in section 3.5, where we are talking about multiple random variables interacting with one another. We're keeping things relatively simple in terms of we're looking at, we're looking at pairs, two or more discrete random variables and 2 or more continuous random variables, but we're not mixing continuous and discrete random variables. So we're keeping them separate still. So this is still not the most complicated version, but it's a little bit more than what you've been taking a look at. So let's take a look at our notes and see a little bit more of an introduction here. So back in section 2.8, we talked about let's see here, clerks that fill an order, a mail order house. Clerks work there, fill the orders. Excellent. So they're Larry, Moe, and Curly filling orders, and they make mistakes sometimes. They told us that 25% of the orders are filled by Larry, 35% by Moe, and 40% by Curly. So that gave us these probabilities. And you may be familiar with these sorts of tables from a basic statistics course. And there they called them the joint probability distributions. So this might look familiar, but essentially what happens is we're saying, all right, what's the probability that Larry filled the order and made a mistake? There it is right there. This probability, we weren't explicitly given, we were given a conditional probability in section 2.8, but from that conditional probability, we're able to calculate the probability that Larry filled the order and made a mistake. This would be the probability that Moe filled the order and made a mistake, Curly filled the order and made a mistake. Again, those can all be found using the idea that the probability of A and B is equal to the probability of A times the probability of B given A. Yeah. So these 2 pieces of information are given in the example, and so we can obtain this information right here. And we found that in that example, the probability that a mistake is made is that probability right there. So we're seeing actually even Bayes' theorem is kind of hidden in here as well. Oh, not hidden. I believe that is Bayes' theorem, section 2.8. All right, so we see this. So what we're demonstrating here is what we already saw. Bayes' theorem said that this plus this plus this gives us our probability of an error. Feel free to review that example again. Okay, but what we want to do with this table is say, all right, well, if this percentage, or this is the probability that Larry filled the order and made a mistake, what's the probability that Larry filled an order did not make a mistake? And we can actually use Bayes' theorem again, because essentially what it works out to be is this plus this should give us the probability that Larry filled the order, because when Larry fills an order, he's either going to make a mistake or he's not. So this probability plus this probability should give us the probability that Larry actually filled the order. So we can fill this entire table in using that idea. So Bayes' theorem got us that number there. And then we can essentially use Bayes' theorem again to fill in this number here. Bayes' theorem with some subtraction anyway. But essentially 0.25 minus this number is going to give us 0.2475. And then 0.35 minus that is going to give us 0.329. 4/10 minus that is going to give us 0.392. And then Bayes' theorem again, the probability that we're not going to make a mistake would give us 0.9685. And then if you added all these probabilities up and added those probabilities up, of course, either you're going to make a mistake or you're not, or one of these three people are going to fill the order, and you should find that to have a probability 1. Okay, so our main interest for this section is actually going to be the table, not the entire thing, but just a portion of this table. Our interest is in this thing right here. Okay, the other portion of that, this larger table here and here, this column, that row, those are going to be considered in section 3.6. So for this section, we're just interested in this. Again, this section is the multivariate distributions. So this is the probability distribution of this variable and this variable, variable clerk and variable mistake. Now, how does this relate? This example does relate to discrete random variables. And for a function to be a discrete random variable, let's see, yep, I believe that's the right way to say that. What we need to have is we need to have that it's taking on numbers. So we would want to have, discrete random variable is a function. So these need to be numbers. So we could say that we can let, let's use a different color here. We could say that we have, yes is a 0, and no is a 1. Larry is 0, Mo is 1, Curly is 2. Using that, we can come up with, call this variable x, call this variable y, and now we have discrete random variable x and discrete random variable y. Okay, and this is their probability distribution. So what we're looking at when we consider these probabilities, okay, so this probability right here, this is the probability that the random variable x takes on the value 0 and that the random variable y takes on the value 2. Excellent. So it's a probability distribution for these two probabilities. Okay, when we have more than one probability, it's actually called, or more than one random variable, it's actually called a joint probability distribution. And we'll see that on our next video. So just as another example, this probability is the probability that the random variable x takes on the value 0. Oh, sorry, I think I maybe said those wrong. Yeah, sorry, x takes on the value 1 here, and y takes on the value 2. Oh no, that was right. That wasn't right. I just said it wrong over here. X takes the value 1 and y takes the value 0. Excellent. So in this case, 0.008, and in this case, 0.2475. Excellent. So again, by assigning the people or just assigning mistake or not mistake numbers gives us a discrete random variable. So it's a little bit weird, right? We're identifying people with numbers and yes and no with numbers, but that's pretty common. If we wanted, that discussion could go a little bit further, but just that is more than sufficient for this section. So this gives us the idea of a joint probability distribution. If we wanted to, we could also think of this as the probability that the event Curly occurs and the event yes occurs. Okay, these are the same thing. Probability that the random variable takes on the value curly, probability that the random value takes on curly and takes on yes. Okay, I said those backwards. Yes and curly. Anyway, I think you get the idea. So probability, joint probability distribution for two random variables. All right, that's all that I wanted to share for this video. Lots of videos to come for this section. So I'll see you guys back in the workshop shortly for our first definition and example.